All right. Hi, everyone. I'm Max Bertolero from Danny Bassett's lab at UPenn. Following that great talk by Alison Gopnik, we have, I'm sure to be another great talk by Ryan Adams. Ryan studied electrical engineering and computer science at MIT, and then did his PhD in physics at the University of Cambridge. He's now a professor of computer science at Princeton University, where he runs the Laboratory for Intelligent Probabilistic Systems. His work is both applied and practical, but also conceptually novel. He works on problems from compression to novel optimizations of machine learning algorithms, as well as the conceptual links between these two problems. He has done a lot of work making it easier for non-specialists like me to apply complex machine learning algorithms, including founding the company WetLab, which was later acquired by Twitter. Finally, he has combined probabilistic graphical models and deep learning methods in order to develop new LEDs and to identify molecules with particular desirable medicinal properties. Today, he is going to talk to us about that combination. Please join me in welcoming Ryan Adams.
Thanks. So today I'm going to tell you about kind of a particular viewpoint on how to combine probabilistic graphical models, which are good at kind of one set of things, with deep neural networks, which I think of as being good at an interesting and complementary set of things. So, of course, it's a very exciting time for machine learning and artificial intelligence. We sort of figured out, after many years, how to really make neural networks work on all kinds of things, and so there's been rapid advances in solving all kinds of things that felt like they might be very, very hard, from self-driving cars to the game of Go to speech recognition, all kinds of scene understanding and generative models and many other things. Looking through the proceedings of this conference, of course, people are well aware of these successes. I think it's useful to just take a step back and ask the question, after decades of interest in neural networks, why is it that they seem to be working now when maybe they didn't work as well in the last kind of great wave of this, like in the early 90s? And I'm sure there are many people in the room that have strong opinions on this, but I think one thing we can agree on is that we have vastly greater compute resources now than we did then, Moore's law, but also things like GPUs, and really interesting specialized ASICs, specialized hardware for training and using neural networks, things like TPUs and kind of many different startups have been developing hardware. Of course, we now also have web-scale data. A lot of the problems we want to tackle take advantage of huge, tens of millions of images and enormous text corpora and speech corpora and many other kinds of things. And so these are very data-hungry algorithms, and lots of data and lots of compute makes it possible to do things maybe we couldn't do before. There's also some new technical insights, right? We now understand the structure of some of these problems and how the architecture relates to optimization and many other things that maybe we didn't understand as well in the early 90s. Things like, are we at local minimum when we're training, or are we in saddle points? What's the effective regularization? What's the implicit regularization of stochastic gradient descent and so on? And of course, interest begets interest, and there are now a lot of companies that believe there's interesting ways to monetize these types of algorithms. So there's a lot of economic interest, pulling many people in from kind of what might have been the periphery of machine learning before. Conferences like NIPS are now, thousands and thousands of people that sell out in like 10 minutes, whereas, just a few years ago, it was sort of an order of magnitude smaller. So really, a lot more people thinking about these problems leads to interesting advances. But I think there's a couple of other things that at least for me, I think are quite important. And so one is that I think that a lot of the successes that we see now have been focused on invariant structures, whereas maybe 20 or 30 years ago, people were thinking about very general purpose architectures and multi-layer perceptrons. So what I mean by that is that I feel like there's an argument to be made that we shouldn't be calling it so much deep learning as we should be calling it convolutional learning. That there's a lot of, the composition is certainly important, and layer structure is, I think it really is important, but a lot of the problems that it feels like we're making a lot of success on here are things in which you can identify kind of compact parameterizations that make it easier to build, sort of take advantage of known structure and generalize. So the obvious thing is convolutional neural networks over images. where a cat is a cat, no matter where it is in the image, but also the meaning of words is something that we kind of expect to be roughly translation invariant within text corpora, same thing with speech. And then we've also generalized these ideas to other things like molecules, where maybe some molecular substructure has a particular function that's invariant to where it is on the graph. And so, as a sort of probabilistic modeling guy, I sort of then attribute some of the successes of deep learning to to sort of taking advantage of what, in some ways, are very good priors for the kinds of data that we care about. And I apologize if my voice is a little sketchy. I have a kid in daycare, and so I'm in the middle, the inevitable sort of perpetual daycare cold that you get as a parent of young children. The other, I think, thing that we often don't appreciate so much about the rise of deep learning is that the tooling that we have available to us now is really a lot better than it used to be. And so, in particular here, I mean things like automatic differentiation. So machine learning has finally kind of really rediscovered automatic differentiation, which has been around, of course, itself for decades, but now we have tools like TensorFlow and PyTorch and many other things that really make it possible to explore an interestingly large subset of the kind of deep learning architectures of interest in a single kind of API. And it's interesting to think about sort of how it used to be in machine learning, where, so here's just a randomly selected paper from NIPS 0. I don't know if you knew NIPS is a zero-indexed conference, but it is. And so from 1987. And it follows a typical pattern that I feel like we've seen in machine learning for many years, where you come up with a new idea, a new loss function, a new architecture, or whatever, and then you're going to spend a lot of your paper deriving gradient rules, right? Deriving update rules. That's like the big intellectual contribution. Look at the calculus I can do. But computers are good at calculus, it turns out. And so now, if I Google something like machine learning without math, I get 180 million results. This is the thing, right? You can do all this stuff. You don't have to prove your worth by being able to derive all these gradients. You just use autodiff, and it'll do it for you. So I thought I'd take a quick sort of diversion here and talk about exactly what these tools kind of look like, just to sort of explain, because I'll come back to this a little bit later. So deep learning, we use these compositional structures, like layered neural networks. And the idea, broadly speaking, right, is that we're going to take our cat image, apply a richly parameterized function to it, get an output, apply another richly parameterized function to that, and then do that a bunch of times until we get to the output, and then we apply a loss function to that output, and we want to compute the gradient of that loss function with respect to something deep in the network. And of course, compositional structure, we pull out the chain rule, right? And what we wind up with is a product of a bunch of Jacobians. And these are sort of vector functions buried deep inside, and so I'm representing those Jacobians as kind of matrices. And then at the end, you just have this scalar output, the objective function, and so I'm representing that Jacobian, that gradient, as a vector here. And so the name of the game is computing this product. And the kind of the good old-fashioned way that you might think about it, that if you sort of think about computing the chain rule sort of left to right, at least like I learned in calculus, then you sort of do this thing where I sort of multiply the first Jacobians and then the next Jacobian, then the next Jacobian going sort of left to right. And this is a kind of a forward pass through these things. And if you think about in the case where we have a lot of parameters going down to some scalar, then this is going to be a sequence of matrix multiplies, right? Which, roughly speaking, is going to be something kind of cubic, right? The trick of backprop and the trick of reverse mode automatic differentiation is to observe that these kinds of things are associative, so I could go right to left instead if I wanted to. Yeah? And so now I have a matrix vector multiply, and that's something more like quadratic. And if I do that, then I get another vector, and then I get another matrix vector multiplication, and I get another vector, and so on. And so now I'm looking at something that is sort of quadratic instead of cubic, and that feels nice. So that's kind of trick number one, in a sense, for thinking about kind of what's the big sort of backprop story. But of course, the really interesting thing that has changed since NIPS 0 is that now we have really nice computational abstractions for doing that computation. It's one thing to just do it backwards and efficiently. It's another thing for somebody else to have done a bunch of the math and made tools that you can just focus on imperatively defining this forward structure. So here's an example from an automatic differentiation tool called AutoGrad that we developed in my group. And the thing to look at is that this is basically just like NumPy code like you would normally write, and then buried inside here are some things that look just like really simple kind of NumPy calls. You'll notice at the top that I'm importing something that is not NumPy, but autograd.numpy. And now I just very easily get the gradient of this thing as a function handle for free, and I could take the gradient of that and so on. And the point here is that somebody else has done the math, and so you can just write code. So you just write imperative code. If you have something really weird and fancy, you can add it. But in particular, these guys have already sort of done the work of remembering what the calculus is for all of these primitives that live inside NumPy, and then you can just get to work writing things. So this is kind of this is kind of one among many abstractions, but this is kind of what I think I think this is an underrated. This concept is an underrated factor in the emergence of deep learning. It's just really good tools. So what is deep learning not good at, right? Well, it's not good generally at reasoning explicitly about uncertainty, right? Representing, kind of knowing what it doesn't know when it learns stuff from data. It's not generally good at producing interpretable models, right? You get a bunch of goo. You get a bunch of neural network goo. It's going to be good at prediction, broadly speaking, but it's not necessarily going to be something that you can look inside and investigate. Obviously, a lot of people are interested in that and figuring out how to do that, but it doesn't want to do it naturally. Closely related to that, it tends to not play well with identifiable parameters. And so here I mean kind of statistical identifiability, where I want to have variables in my model that correspond to particular physical quantities in the world. Maybe I have an economics model or some scientific model, and I want to know, I want to estimate a particular number among many parameters of a really big neural network. Similarly, it's quite hard to build in a lot of structured a priori knowledge. So I talked a little bit about convolutions and invariance. That's a very nice kind of a priori knowledge, but it's one particular kind of invariance, and there's many other kinds of things you might like to build in, right? You might have some knowledge of a certain latent variable structure, for example. Also, in general, deep learning being very data hungry, it doesn't necessarily work well in small data regimes. And a lot of the problems you care about in science and engineering and in the real world don't necessarily have web scale data associated with them, and yet you'd still like to be able to make sort of interesting progress and train interesting models. And then the other thing that I think we now understand doesn't happen very well with deep learning is the uncoupling of architecture and learning. So I think there's this idea that sort of machine learning purists, for lack of a better way to put it, is the idea that I can sort of write down my model, write down my inductive biases about the world and so on, and then I have an optimization procedure or some fitting procedure. And these are two separate things. But it's become increasingly clear that deep learning doesn't do that. That you can take the same model and train it to convergence with two different optimization procedures, both of which give the same training loss on the same model, and they will yield wildly different generalization consistently across those trainings. And this should be kind of worrying to us, that somehow these things are coupled. We'd like to uncouple them. And so you might look at this and kind of get where I'm going, because these look like the kinds of things that probabilistic graphical models are good at, right? Everybody remember probabilistic graphical models? Yeah, they're sort of out of vogue. I feel like they're sort of dated. But I think who cares about these things now? But I think there's something really important to remember when you're methodologically centered. Like a lot of us in this room think a lot about methods, right? And we like to develop the next coolest thing. But it's really important to decouple in your mind what's hot in a methodological field from what's successful and useful, right? Like there's not a ton of papers written about linear regression and NIPS, right? But linear regression is still a really good idea, right? And so I think probabilistic graphical models are kind of in a kind of consolidation phase like this in some ways, where they're good at a lot of different things, but people aren't actively, they're not the hot thing that young grad students are excited to work on. Nevertheless, let's just talk about the kinds of things that, just to sort of remind ourselves of why these things are good at that stuff. So everybody's got a phone in their pocket, everybody's got a laptop. These things are doing forward error correction. So when you store data or you transmit data, it's going to be subject to noise, and so things like low-density parity check codes are important for all of your devices actually working in the real world. These are often framed as graphical models, and some of the best decoders for these are essentially belief propagation. All right, so these are probabilistic graphical models, sort of in heavy use all the time. I think it's also helpful to remember that Kalman filtering inhabits many, 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 many devices, from the sort of airplanes that you might have flown to get here, to medical devices and your GPS and lots of other things beside Kalman filtering. These are linear state space models that we often reason about using sort of as graphical models and using graphical algorithms. And then, of course, the world is full of these various kinds of bespoke probabilistic graphical models where they are still the sort of the best way to solve different kinds of problems. Some kinds of recommendation systems and like gaming, matchmaking online, and protein structure prediction, and a variety of other problems. So it's kind of helpful to just keep in mind that these are still sort of useful and successful things in ways that are interestingly orthogonal to kind of what deep learning is all about. And so let's talk about what those things are. Well, the big thing that frustrates you if you deal with probabilistic graphical models is that they're not necessarily good at very high dimensional data, and they're not very good at situations where you have a lot of data, right? So these are kind of situations where your design matrix is getting big in either direction or both directions. And it boils down to the fact that it's often difficult to construct likelihoods that you like that can handle very high dimensional spaces. And it's also hard to perform inference, whether it's Markov chain, Monte Carlo, or something else, use in places where you're going to have very high dimensional kind of posterior spaces. And part of the reason for this is that, unlike a lot of optimization algorithms and things that have been successful in deep learning, many Bayesian inference algorithms that we like to use need to look at every single datum, every single iteration, right? That's not always true, but it's often true for things like Markov chain Monte Carlo. And so there's this kind of intrinsic scalability challenge as the data sets get bigger. And then finally, and this is in contrast to what I was saying about automatic differentiation earlier, the tooling for probabilistic graphical models, and I think is sort of really lags automatic differentiation, whereas the kind of things you want to build in deep learning are very well served by tools like TensorFlow, and most of what people want to build, they can kind of construct in that or PyTorch or something. There exist, probabilistic programming systems and things like Stan that you can construct probabilistic graphical models in, but they don't necessarily sort of serve all the kinds of models you want to build extremely well. And it's certainly far from being the case that if I had some complicated bespoke model that I could guarantee somehow that those would work, whereas TensorFlow probably will solve the sort of deep learning architecture that you want to come up with. So what I'd like to figure out is how to kind of get the best of both worlds here. Like, how can we construct, since I view these as being complementary kinds of capabilities, how can we build single models that include all of these things? So how can we model large high-dimensional data sets? How can we exploit things like convolutional structure to improve inference? But at the same time, how can we build in other kinds of a priori model structure that we might believe about the problem we're trying to solve? And kind of along the same lines, exploit things like dynamic programming to be able to do a better job of leveraging graphical structure across latent variables. And then once we've done that, can we figure out ways to have interesting models that can handle sort of big high-dimensional data, but still provide sort of useful estimates of uncertainty and give us maybe useful ways to reason about model selection. Hopefully these would also solve this issue with decoupling and fitting, although I think this is a problem that we're not very close to addressing. And ideally we would have kind of one API, right? Like one way to be able to do all of these kinds of things, and so that would serve many of the different kinds of models you wanted to build, whether they had kind of graphical structure, probabilistic structure, or they looked more like traditional deep learning models. So, of course, this is like a particular view I'm going to talk about, but it's by no means the only view. There are just a tremendous number of interface points between probabilistic modeling and deep learning, more than I could possibly elaborate upon today, and they go back. I mean, as long as people have been thinking about sort of connectionist architectures, people have been thinking about probabilistic connectionist architectures and Bayesian variants thereof, right? So a really salient example of this, of course, is our Bayesian neural networks, which go back to the late 80s. So essentially, people were thinking about Bayesian variants of these things almost immediately after the backprop paper. And I feel like this kind of, so this is where, of course, you want to estimate posterior distributions associated with the parameters of a big neural network, or I guess in these cases, a small neural network. But and sort of be able to reason about uncertainty and maybe push that through to predictions. I feel like this kind of hit an interesting intellectual peak in the early 90s with the PhD theses of David Mackay and Radford Neal. But this is something that people care about now, and maybe care about even more now. There's probably a much bigger community that cares about it now. There's the Bayesian Deep Learning Workshop at NIPS, and I think there's a Bayesian Deep Learning Summer School. This is something that's still ongoing, but again, it has a very long history as one point in the sort of interface between these things. I think related to that, another thing that people care a lot about, and on the sort of probabilistic side of things, is this Bayesian non-parametric model called a Gaussian process, which is useful for regression and classification and all kinds of it sort of makes its way into all kinds of spatial statistics and other things. And I think it's worth remembering that the reason machine learning began to care about this in the 90s was because Radford Neal's PhD thesis observed the Gaussian process is the limit, or it can be constructed as the limit of a multi-layer perceptron with an infinite number of hidden units. And so people sort of got excited about following that up, and then Gaussian processes kind of became their own probabilistic thing, somewhat decoupled from the way we think about neural networks now. And then, of course, I think another thing that kind of has to come up when we talk about this interface between deep learning and probabilistic graphical models is the Boltzmann machine. So this has been around for sort of as I guess kind of at the same time as we've been thinking about multi-layer perceptrons, people have been thinking about these kinds of undirected graphical models that are used for unsupervised learning. And on the right here is a restricted Boltzmann machine variant. But the point here is that we think of these as being neural network kind of architectures, and they're nevertheless explicitly defining a probability distribution over data. And historically, it's also sort of worth remembering that there's a sense in which RBMs are kind of, like research on RBMs is kind of the reason deep learning happened in this particular incarnation. So around 2006, E.Y. Tay and Jeff Hinton and I think Simon Ozendero published a paper about unsupervised pre-training from data and then using RBMs and then stacking those and then backpropping through them and observing that they got much better results with big neural networks. And it was those kind of early results in some ways that kind of led to to everything crazy that's going on now. NIPS having 5,000 people and so on. And so, so this is just kind of one more example of this interface. The kinds of things that I've been thinking a lot about the last couple of years, and I again want to emphasize, like lots of people are thinking about many different versions of this, but I get excited by applications and trying to tackle applications that kind of motivate my methodological research. And so I find there to always be this kind of need in many, many problems for trying to come up with really flexible, massively parametric models that nevertheless have interesting sort of potentially identifiable and interpretable structure living inside and that help me come up with reasonable uncertainty estimates. So as was mentioned in the introduction, one of the things I'm interested in is automating the process of design, so inventing new things using machine learning. And this is a place where I think a lot of, where on one hand you're talking about possibly very complicated structured objects that really benefit from deep learning architectures, but you're also talking about situations where you're going to have limited resources to evaluate those designs, and so you really want to do something interestingly sort of information theoretically optimal at the top. So we've had some success in doing this with organic photovoltaics, so, and in particular with organic LEDs, actually sort of designing new things and resulting in new materials. But then we've also been looking at things like designing proteins, in this case, like the green fluorescent proteins. But that's not the only sort of place where I think these things come up, and where, again, just taking a sort of a personal view of things we've been thinking about the last couple of years. In sports analytics, I think this kind of semi-parametric view comes up quite a lot. We want a really flexible model to maybe capture something complicated like how Steph Curry decides to shoot his baskets, But we're going to ultimately need to be able to come up with something compact, low-dimensional, interpretable if you want like an MBA front office to be able to use it, right? And so I think these are kind of examples where you have something complicated that you need a lot of parameters for, but you're going to need but for it to be useful, you're going to have to bake it off into something you can understand. A sort of, in some ways, a little bit more serious example, but I think really highlights these things well, is some work we've been doing with astronomers on the West Coast and statisticians at Berkeley to try to build a probabilistic catalog for every light source in the universe. The motivation for this is to drive a new device called the Dark Energy Spectroscopic Instrument. That won't surprise you, is to find sort of the dark energy. But this is a situation where we have a huge amount of data and possibly quite complicated high-dimensional objects like shapes of galaxies or the spectral energy distribution of a quasar, kind of things where you want to throw a lot of sort of non-parametric goo at something, but at the same time you have quantities that you really need to understand, right? You want to estimate redshift. And that's not something that can just be some weird interpretable piece of a neural network model. There needs to be a number called redshift associated with these light sources for you to understand kind of where this thing actually is. And so again, it's a situation where a big probabilistic graphical model is one part of things, one part of kind of what you'd like to have, but it needs to have very flexible, very flexible stuff built into it. The last thing, and this is kind of what I'm going to talk about in this kind of vignette, I'm going to go into more detail here, is think about quantifying animal behavior. So this is where we want to build, we want to do unsupervised learning, unsupervised segmentation, identification of the dynamics of, for example, mice in service of neuroscience. So this is what I'm going to kind of zoom in on a little bit more here. And before I go any farther, I want to say that this is. I am not a neuroscientist, but Bob Data, and this is in collaboration with Bob Data, and they're kind of his mice, and this is in many ways his brainchild, but it was a really fun thing to get involved in, and as I said, it's kind of helped drive me and my group's methodological agenda to get better at these kinds of problems. And I should also mention his grad student, Alex Wilczko, and then my postdocs, Matt Johnson and David Duveno, were really at the heart of the work I'm going to tell you about. So this is a little bit of a silly motivation to give to this crowd, because often I talk about this work to machine learning people, and so, okay, we build mouse models for things, and these are important, and we want to understand the brain with mouse models and things like that. This crowd probably appreciates that quite well already, but the motivation here is that we want to have a naturally behaving mouse, and we want to think about how we can quantify the effect of drugs or optogenetic modifications or introducing fox pheromone or whatever it is we want to modify about its environment or itself, and talk coherently and reproducibly about what it does differently. The one view on this, right, maybe the kind of, I'm going to use the word classical here, but one view on this is to try to take something complicated like mouse behavior and come up with a quite simple way to measure something that hopefully relates to the quantity that you care about. Everybody knows what this is already, maybe in this crowd? I don't know. Some people. Okay, this is called an elevated plus maze, and as I understand it, anyway, the idea is that there's a region of it that is kind of exposed, and there's a region of it that's kind of inside walls, and that if a mouse is anxious, it likes to spend less time on the exposed portion. And so if you're trying to develop an anti-anxiety drug, then you could measure its effect by asking what proportion of the time does the mouse hang out on the exposed portion versus in the walls. That's nice. It's a scalar. I turn this possibly complicated mouse into one number that I can use to summarize its behavior. But of course, we think humans are complex. The point is these are models for human behavior, and so if we boil off, and we don't like to boil off human behavior into really simple things, and so let's try to not boil off mouse behavior into really simple things, and try to come up with maybe more nuanced understandings of how things vary. Now, of course, again, there are a lot of people who think about this, and there are a lot of different ways you could tackle the problem. One obvious thing to do is to have a grad student label a lot of frames of video, right? And the problem with that, it turns out, is that, well, for one thing, that requires coming up with human labels, right? Coming up with human language to describe what the mouse is doing. That's necessarily anthropocentric. What the mouse does doesn't care how you describe it. I mean, with the big asterisk that ethology is a serious thing. But then also, it necessarily involves some time scale that's going to make sense for the human, but that again may be irrelevant for the mouse. And in any case, even if you feel good about sort of describing the behavior itself, empirically the inter-observer error rate is like 50% or something for this. So it's very hard to get something reproducible. The hope here is that we can take advantage of better instrumentation, all of these fast models, GPUs, like the whole sort of deep learning framework that has made it possible to solve Go. Maybe we can repurpose a lot of these kind of really great results to go after unsupervised discovery of sort of mouse dynamics. And this is a depth camera view of a mouse with infrared. This also has a nice property that mice like being in the dark, and so you can have them in the dark naturally behaving if you use like a Kinect in this case. And so that's kind of the name of the game here. And we think of this as being a task of trying to learn a language of behavior. We imagine that individual mice and across a population of mice, there are discrete bouts of behavior of some kind of like characteristic duration, and that there's interesting dynamics on that discrete space. And we can think of these as kind of syllables of behavior. And by analogy you can kind of think of this problem as being sort of like, if I had a bunch of raw waveform data of people speaking, could I discover syntax from that? Could I discover meaning in natural language from like raw waveform recordings, okay? And it's just here we're going to do depth video instead. And the point being that if we can have this now richer summary of what the mouse is doing, then we can evaluate how those dynamics are modulated if you shine a laser into its brain or introduce it to fox urine or whatever it is that kind of informs your scientific hypothesis. So when you sort of put your graphical modeling hat on and you kind of think about how you want to frame this, it's natural to come up with something like a switching linear dynamical system. So the switching linear dynamical system is this idea that we're going to write down a model with discrete latent states, and that there is some evolution over those latent states. Then this is kind of the name of the game: discovering what those states are and discovering what those dynamics are. But of course, the mouse isn't discrete, so we're going to have to map that to the actual observations. And so a switching linear dynamical system also has a set of continuous variables where there are linear dynamics over those continuous variables, and the particular dynamics are determined by what discrete state is currently being inhabited. Okay, so blue circles are giving us sort of blue continuous dynamics. You think of the continuous dynamics as kind of being mouse physics, right? That these are the joint angles and how they interact, and that's what those are trying to learn. And then the idea is that on somewhat longer time scales, you have these these discrete syllables. And so we can write that down into a sort of somewhat traditional probabilistic graphical model in which we have continuous latent variables and discrete latent variables, and then we're going to have some overall parameters that we're going to add to that, the kind of the global variables of this thing, and we're going to try to explain the actual depth images in terms of using those continuous observations, those continuous latent variables. And a natural kind of thing you would do here, if you're a sort of graphical model guy, is you'd say, well, let's model these are continuous observations. Let's make them Gaussian. But the problem is that that will not work, basically, right? That individual mouse frames, the distribution of these mouse frames, they're just not Gaussian, right? And then like nothing is Gaussian, but these are definitely not Gaussian. And even and they're super high dimensional, and big Gaussian mixture model type things don't work in high dimensions because they're really hard to fit. And what happens, right, is that because you have this kind of impoverished local distribution, then if it wants to explain complicated behavior, it needs to tile down a whole bunch of these Gaussians. And so you wind up with a lot more states than you necessarily really kind of believe, right? So a kind of a cartoon to kind of think about what I'm saying here is that imagine we have this toy data. Imagine that every one of these dots here is like a frame of this mouse video. And there's some unambiguous discrete structure here that you could imagine being the kind of the thing we'd like to discover. And, but those kind of clusters have a funky shape. And if you apply a vanilla Gaussian mixture model, you pull out your book by Chris Bishop or whatever, you fit the thing, you'll get something like this, which models the density quite well, right? Like it captures the interesting mass that this density has, but it completely destroys the interesting potential interpretable structure that lives there, right? Because the Gaussian isn't rich enough for the individual components, and so your model-based clustering just divides it up arbitrarily. And now if I go in and look in and try to ask, like, how are these frames of video grouped, then I get answers that don't really necessarily make sense. And this isn't like a hypothetical. Like this really happens in lots and lots of data because it's hard to come up with likelihoods that make sense for the data for whatever problem you have at hand. On the other hand, you could say, well, no, man, we threw away all that Gaussian mixture model stuff. Like, let's do your favorite deep density model, right? And what I'm going to do is take a Gaussian distribution and I'm going to warp that with a really flexible, massively parametric neural network into explaining that density. That will also work, and it will model the density quite well, but it's destroyed the discrete structure in a different way, right? Now we have a bunch of mush. We have lost this kind of interesting discrete stuff that is what we're ostensibly after. So what we want is some kind of sweet spot, right? We want to find some place where we have interesting discrete structure that is modulating a highly flexible local model, right? That's the name of the game. And so when I talk about, in this instance, trying to sort of bridge this gap, this is the kind of thing that we'd like to be able to do. Is have one model that's going to have some interesting, in this case, like a mixture kind of graphical structure, but then flexible component densities. Going back to the mice, I like to think of it kind of like this, where if we have like an elevated plus maze, that is, we take our complicated data and boil it off into something simple, then we can use simple models and they will fit, but we're always going to be constrained to evaluate simple hypotheses, right? On the other hand, if we come up with, we tackle complex data with sort of equally complex models, then we're not necessarily going to wind up with new understandings. We might be able to, simulate new frames of video, right? But we can get undergrads to take video of mice already, right? And so we don't need new frames of video. What we want is to understand the data we have. And so broadly speaking, we'd like to find a way to build models that couple sort of interesting, hopefully interpretable discrete structure with big flexibility, kind of in a sort of parsimonious way. And getting back to the idea that graphical models and deep neural networks are sort of interestingly complementary technologies, then we can see that they will kind of help us in two different ways. And in that we're going to be able to use neural networks in a model like this to come up with better ways on the sort of generative modeling side to come up with sort of better distributions than Gaussians. And then it will turn out that you can use neural networks to also perform better inference, that they can help you, they can kind of help you do better, kind of actually learn the data better and actually kind of estimate these quantities using neural networks as well. So neural networks are this enabling technology in a sense, whereas I think, at least for me, I felt like a lot of sort of probabilistic graphical models have been bouncing off of this kind of high-dimensional barrier, right, where it's very hard to tackle these kinds of problems, but in a kind of marriage with neural networks, then we can, then it becomes possible to go after things that we couldn't go after before. So let's talk about that left piece first. So this is actually kind of simple and straightforward, and again is an idea that has been around forever, which is rather than just having a simple conditional distribution that's a linear function of the latent state, let's make it a nonlinear function of the latent state using a deep neural network. So rather than just having these continuous latent variables, the x's in this case, parameterizing the mean and variance of a Gaussian, we're going to push them through a big neural network, and all of a sudden now our conditional distribution is potentially much richer, right? So that's kind of almost too easy, but it does give us a kind of a recipe for thinking about how to put these things together, where we don't necessarily have to even worry about state space models and kind of the nature of these complicated things like switching linear dynamical systems. We can just think about sort of cartoon, simple models that have some kind of interesting conjugate prior exponential family stuff on top, and then some kind of interesting neural network observation model sitting beneath it. And switching linear dynamical systems and mouse observation models are just one example of that. But kind of the point here is that when you take that view, then we could stick interesting neural network models on top of your favorite graphical model, no matter what it is. So you could go back through and say, oh right, canonical correlation analysis. Well, now I can have this kind of direct generative interpretation with a deep neural network observation model in CCA or LDA or whatever your favorite sort of old school graphical model is, for lack of a better word. The problem, it will not surprise you, is that it's very easy to write that kind of thing down, but it's much harder to actually come up with a way to fit it. And so I'm going to spare you most of the details and kind of give you pointers to other things rather than kind of taking a deep dive on this. But the cartoon is that, or the high-level picture is that we can do mean field variational approximations. And that just means we're going to build a simple factorized approximation to the posterior distribution. That'll let us reason about this quantity we care about, the marginal likelihood, by maximizing a lower bound on it and turning inference into an optimization problem. And then by using this really great work on stochastic variational inference by Matt Hoffman and Dave Bly and other folks, then we're able to sort of treat that as a problem in which we take subsets of data and compute gradients on those and are able to fit variational posteriors using that. And so that should kind of hint at the idea that we could have this unifying API where automatic differentiation lets us do deep learning and lets us do variational inference. And to be clear, that's not a new insight that you can do variational inference with automatic differentiation. The point here is that we can kind of put it all together in one piece, and it turns out that a lot of the sort of dynamic programming computations that you would do in service of conjugate structure can be done, sort of turn out to fall out of the computations you would do with automatic differentiation. So just taking a quick minute to kind of talk about the structure of this problem. So we have some graphical model on the left that we care about. On the right is a factored posterior where there's two kinds of things. There's local variables that I'm writing as blue, so these are like per frame data, and global variables that here are in black. The name of the game is to learn those global variables, right? Because they're describing the kind of population structure of mouse dynamics. And so we're going to approximate this posterior distribution with this factored Q, and then write down this lower bound that you can just think of as trying to answer the question, how do I find the parameters for Q that make it closest to the true posterior in KL divergence? Part of the insight of sort of Matt Hoffman and colleagues was that you could take these local variables and you could perform this sort of local optimization and reframe the problem entirely in terms of the global variables, and that now you are, and that it turns out that you get sort of very nice geometric structure where you get the natural gradient, which is kind of the gradient with the appropriate Riemannian metric, just by looking at the expected sufficient statistics under that distribution. And also you can, if you have multiple sets of these data, then you can subsample them and get this nice natural gradient as well. If you don't know what I mean when I say natural gradient, it really just means like a gradient that for a probabilistic model is invariant to the particular parameterization you picked, and so somehow kind of knows about the probabilistic structure better than gradients just in the kind of the actual parameters you wrote down. So just a better gradient, let's call it that. And so the way we kind of use these things, right, is we have our data. They give us some local evidence potentials via the likelihood, right? That gives us our local factors. We then perform some dynamic programming across these things, right? Some message passing to get these expected sufficient statistics. And in the case of stochastic variational inference, this gives us exactly kind of the direction to go in the global parameter space. The problem, of course, is that once we hang a really big deep neural network off of the likelihood, then things are going to get weird, and we're not going to be able to easily compute these expected sufficient statistics. And so this really sort of clever idea that is generally called amortized inference is to say, well, rather than trying to perform this local optimization to estimate that wonky posterior, I'm going to use some function approximation that looks at the data, that in this case, like literally looks at the image of the mouse and tries to guess what the variational parameters are, the local variational parameters are. And Who's got a big, flexible function family? Neural network guys, right? Like, so we can take a neural network, and your favorite convolutional neural network now looks at an image and produces an estimate of these latent variables. So this is called a variational autoencoder, which Dirk Kingma and Max Welling introduced a few years ago. And it's a really interesting kind of reconstruction of the idea of an autoencoder. So autoencoder is this idea that goes back decades of building a neural network for unsupervised learning that learns the identity function, right? That goes from, say, takes an image, tries to find some low-dimensional representation of it, and then decodes it again. And the variational autoencoder reframes that encoding step as a variational inference, right? It tries to estimate some parameters, and the decoding step as a likelihood. And so you can see how these two neural networks I mentioned kind of are the encoder and decoder of a neural network, where now we just have a highly structured sort of latent space. So this gives us a kind of a dichotomy, or I guess a trichotomy here, that where on the left we have sort of natural gradient stochastic variational inference, where if you have very nice structure, then you get optimal local factors when you do variational approximations. You can ask arbitrary sort of marginal queries, and you kind of get a lot of nice properties, but you can't tackle highly nonlinear likelihoods. Variational autoencoders give you this view where it's going to be fast, but it's always going to be suboptimal because you're doing this amortized inference thing, and you're not necessarily able to ask arbitrary marginal queries. The idea here is to have something called a structured variational autoencoder, where you have where it's going to take advantage of the graph structure when possible, allow you to ask arbitrary marginal queries kind of up to the resolution of your amortized inference, lets you do natural gradients for the parts where it's possible, and exploit, again, that conjugate graph structure where it's possible. So trying to kind of find a sweet spot between fully amortized inference and natural gradient stochastic variational inference. So the idea being, now we have now we have our observations. Now we have a neural network that is going to produce the evidence potentials directly. All right. So think of it as just actually, instead of getting those from a likelihood, we're going to get them from this recognition network. And now we can still, once we have those, run our favorite fast message passing algorithm, and we can now do the so-called reparameterization trick to get gradients for updating that neural network, and can take natural gradient steps in the global parameters of a probabilistic graphical model. So we can kind of split these things apart. So going back to this little pinwheel picture, then the way to think about what's going on here, actually, even though probably the last couple slides seem kind of weird and complicated, the way to think about it is that I have these observations on the left, and I have the latent space on the right. And what I'm doing is I'm looking for the neural network warping that makes the Gaussian mixture model work. Right? The Gaussian mixture model is really simple, and if I can, so if I find some nonlinear warping, then I can kind of reshape it so that it sort of does the right thing for these more complicated data. And we can look at, we can do the same kind of thing with more interesting dynamics models. So this is kind of like a little one-dimensional bouncing puck. And so it's nonlinear, learns a local model, and then is able to sort of learn the dynamics. Here the red line is kind of, before the red line is things it's seen, and then it's projecting forward what happens after the red line. And going back to the mouse, the way we can think about this is that we're trying to learn some manifold of all sort of mouse depth images, but such that the dynamics are simple. So that if you look at the dynamics restricted to the manifold, then something like a linear switching linear dynamical system makes sense. So how do we find that nonlinear manifold such that simple dynamics explain the data? And we can do the same kind of project forward with frames of video, where on the top here we're seeing the kind of the actual what the mouse actually did after the red line, given the stuff before, and on the bottom we can ask the system to sort of fantasize new mouse data. And we can also kind of get back to the original task of how do we segment out and identify stereotyped behaviors. So here are a bunch of different mice, and kind of these are post hoc labeled behaviors. When the white box comes on, the mice are all inhabiting the same syllable. This is kind of where the mouse is kind of rearing up. This is where it's kind of falling down. And this is where it's kind of like nuzzling its tummy. Okay, so the takeaway here is that supervised learning, deep learning, kernel machines, whatever it is, the name of the game has kind of always been find a representation of your data such that a linear separator works. Even if you've got a convolutional ResNet 100 or whatever, at the end of the day, at the top of that thing is a logistic regressor. Right? At the last layer of your neural network is going to be something linear in your typical supervised learning task. And no matter what your methods are, they're trying to find a place where that linear separator works. Here, what we're trying to come up with is a similar kind of analogy, if you will, for probabilistic graphical models and other kinds of unsupervised learning, where the idea is find a representation where a Gaussian distribution is the right thing, or whatever simple parametric form, find a warping such that your simple parametric form explains the data. So it's kind of a similar idea. Find the basis where your simple probabilistic graphical model works. So I'll wrap up here. Basically, the kind of big picture is that probabilistic graphical models are sort of an interesting complementary technology in many ways to neural networks, and that we can put these together to potentially to get the best of both worlds, because we can use neural networks to go faster, use neural networks to do high dimensional likelihoods, but ask the graphical models to give us nice, potentially discrete, low dimensional structure, and take advantage of kind of all the kind of the awesome dynamic programming algorithms and things for performing inference. I haven't talked about it extensively, but automatic differentiation provides a single abstraction, right? Because we're able to turn these into sort of gradient descent problems in both cases. And so the idea is to have a kind of a single API that lets you learn both kinds of models. And there's a more sort of formal way to think about that I'm not going to talk about today, but to sort of give you a pointer to some other work that Matt Johnson has done on thinking about kind of you can do this with proximal, you can kind of form a single view with proximal operators. I'll stop there. Thank you all for listening, and thanks again to my wonderful collaborators that sort of put this all together. Yeah.
How much sort of smoothing or compression you're going to do for your manifold, into the simpler
Yep.
state-space trajectory. And that seems to be a problem in domains where we don't have strong priors on it. Like, how many behavioral categories are there in mouse's behavioral repertoire? How many are there in mouse's behavioral repertoire in a field or in blocks or in clusters? So how do you think about that problem, or how should we think about that problem?
Yeah, so just repeating so everybody can kind of hear, I'm going to paraphrase, so catch me if I'm wrong. So there's a kind of like a trade-off in the complexity of models, right? I could pack a lot of flexibility into the neural network, or I could build a bigger latent graphical model, right? And in domains where you don't know very much about what that graphical model should be or what your likelihood should be, then you're sort of feeling around in the dark for trading off those complexities. Is that a fair characterization? And that's absolutely true, is the answer. To try to deal with specific questions like how many distinct behaviors are represented in the data, one thing that's nice here is that in addition to the sort of probabilistic graphical model story, we're able to import the Bayesian nonparametric story. So what's actually sitting here are things like Dirichlet processes that are capable of sort of, are kind of assuming a priori that there's an infinite number of possible mouse behaviors, and it's just a question of how many we're seeing in some data. Nevertheless, that doesn't free you from this burden of trying to balance these two things. And on one hand, it's hard, and I don't have a good answer for that. But then also, that's not different from many decades of semi-parametric statistics where you also have this problem. And so, so I feel like it's a problem we all need to understand, sort of in data modeling in general. Like, how do we balance these structure? And given a lack of really good a priori knowledge, I don't have a really nice answer for that. Yep.
Changes between having 2D information versus full state, like you had complete motion capture data for the end.
Yeah, you mean like what? Like, would it be?
Would it be more latent state, fewer? Like, how does
Yeah.
anything change?
So I think this is the answer is certainly, sorry, the question was, if I had full three-dimensional data, what would I learn that was different about the mice than what we learned here? And I think there's lots of behaviors that we can't see. We have this top-down view. It's coarse that you've seen the video. In an ideal world, I mean, my favorite version of this is where you're actually your latent model actually knows about joint poses, is capable of actually rendering a mouse and comparing that to what it sees. Like there's the notion of what that a priori structure is kind of can go arbitrarily deep depending on what you're willing to model. And I think in some ways this is a first pass trying to, where, to be clear, part of the motivation here is to handle this reproducibility issue where anybody can buy a Kinect. Whereas maybe not everybody can buy extremely nicely calibrated multi-pose three-dimensional cameras. But my sort of favorite versions of this structured variational autoencoder would do things like discover pose from unsupervised data, given access to multiple views and things. But we're not there yet, for sure. Yeah. Yeah. So the question is, I sort of criticize deep learning for having this difficulty of coupling the learning with the architecture, and the question is, in variational inference, does this happen also? And the answer is that it does, right? I mean, variational inference is trying to solve a difficult non-convex optimization problem that, in its own right. And so if you don't do a good job with that optimization problem, then, then you may get a different answer. I think the difference between these two things, though, in variational inference's favor, is that no one ever says in variational inference that if I had a worse solution to my optimization problem, that I would be happier, right? In general, if I have that lower bound, I want to make that I want to make it as tight as I possibly can, and I never want to take a looser bound and sort of somehow apologize for the fact that actually my model is so wonky that a worse answer looks better. Whereas in deep learning, that happens all the time, absolutely all the time. That you increase batch size, find a better solution, and yet it's worse at generalization.